Right, folks. Good morning. Happy Wednesday. How's everyone doing?
Pretty good. How about you?
I'm doing all right. I feel like the first week is always very exciting, right? There's all new stuff,
Yeah.
getting the hang of things. It becomes a little less
Yep.
like week 4, but you know. All right. So before we get started with our content today, and we definitely have a lot of content to cover today, but before we do that, I just want to run through a couple updates on Canvas to make sure that we're all aware of some like hours for the tutoring and hours for the office hours, okay? So I'm going to go ahead and share my screen. Okay, so this is the Canvas shell. Let me just change it to the student view real quick so it looks like what you have on your screen. Okay, so last time we talked, just a reminder that the home page takes you to where all of the content is housed, right? So last time in class on Monday, we did 4.1. So if you click 4.1, then everything should be linked now, right? The blank notes that are available before the class, you can print them out, you can upload those to your tablet. 4.1 complete notes, so that's all the notes that I wrote during class so that you can kind of look back on them. I know sometimes, you know, we don't always get a chance to write everything down, or maybe we just want to make sure we wrote something down correctly, so that's why those are available. And then last but not least is a link to the lecture video, okay? So I'll be chunking the video so that it's like everything is always like just 4.1 or just 4.2. So it should be pretty easy to find. So in preparation for today, if we go back to the home page, the goal for today is to cover 4.2, 4.3, and 4.4. Okay, so that's our goal for today, to get through sort of the first half of this chapter. And then next week, we're going to be covering 4.5, 4.6, and parent functions. And then we're going to have our first exam on Thursday of next week. Okay, so that's it for the content reminders. If you go into the logistics tab, okay, this is where you can find the syllabus and the schedule, the Zoom room, the password, all of that information. I know some people were having trouble getting onto WebAssign. I believe that the codes should be getting sent out to you soon, so that you don't have to pay for it. But either way, if you sign up right now, you should be able to access a 14-day free trial. So you can at least get started on the homework that is due on Sunday this week, okay? I did add a new tab since we last met. So if you click on Val's tutoring sessions, so for example, she's going to have a tutoring session today. So if you click on this tab, it gives you the link to the Zoom room. Okay. Now this is not her Zoom room, but this is the STEM Zoom room. Okay. So once you get to the room, you're not going to see Val right away. You're going to see sort of like a front desk person, or what we call the moderator. You just tell that person that you were looking for Val, or that you're there for STEM core, and they will move you to the right place. Okay, so you don't need to do anything other than click on here, tell them you want to see Val or the STEM core program, and then they'll get you on your way. Now, her hours are going to be Mondays from 1 to 3. That was the most popular time on the survey that you all filled out, so thank you for doing that. Now, Wednesdays, a lot of you also said 1 to 3. I chose 3 to 5 because I know that some of you had mentioned that you might not be available until after 4, okay? So this way we can kind of have like an early afternoon and a later afternoon session. Now, I do want to clarify, you don't have to show up for the whole 2 hours. So if you want to pop in at 1 o'clock, and then like leave at 1:30, that's totally fine. Or if you are like, ooh, I have class that doesn't end until 4, like, can I show up from 4 to 5 only? That's totally fine. Okay, so don't feel pressure to stay the whole time. And remember that if you do go to her tutoring sessions, that those are an opportunity to earn some more extra credit. Okay, so every time you show up, she'll take attendance of who showed up. Got to show up, ask her a question, and then you can earn your extra credit. Okay. So her contact information, in case you want to speak to her, like say, hey, I'm going to show up on Monday, could we go over this? You can message her directly through Canvas, or you can email her, and I've included her email here. Okay, so you don't have to write down any of this. It's all right in Canvas for you. Okay. The other announcement I just wanted to make is that I did update the syllabus. So if you go to the syllabus, okay, I know that on Monday it said that my office hours were to be determined, but based on the survey, it seems like most people prefer Monday, Wednesday from 8:30 to 9:30, okay? Now I wasn't sure if folks were gonna be able to see this before this morning, so I'm happy to do office hours tomorrow from 8:30 to 9:30. Okay, so that's Thursday, 8:30 to 9:30. It's going to be in the same Zoom room. If you want to come hang out, do some homework. I always have extra work I need to do, so I don't mind sitting around doing my work while you do your work, and then you can ask me a question whenever you have one. That's totally fine with me, okay? We did have a few folks show up on Tuesday to office hours, and again, it's totally fine to like just kind of be doing your work and have me there to answer questions as they come up. You don't necessarily have to have a question coming in, okay? So definitely come check that out. That's going to be tomorrow from 8:30 to 9:30, but then after that, starting next week, it's going to be Mondays and Wednesdays from 8:30 to 9:30. Okay, and same thing, you don't have to show up for the whole time, but if you have like a really important question and you show up at 9:15, we might not have enough time to finish answering your question before class. Okay, so if you are going to show up to office hours, try and leave yourself enough time that you'll be able to get your questions answered. Okay. All right, are there any questions on Canvas? Well, then I'm going to stop sharing my screen here, and I'm going to go ahead and start sharing my screen again for the 4.2 notes, okay? So if you haven't had a chance to print those out yet or download those, please go ahead and do so. If you do not have the technology that supports that, totally fine. I'm just trying to make folks' lives easier if I can, but if you need to write this on pen and paper, there's nothing wrong with that. No judgment here, just do what you need to do, okay? All right, so here we go. Let's jump right in. All right, so we are on section 4.2, okay? So on Monday, we talked about 4.1, which was just the basics of exponential functions. And now we're gonna dive a little bit deeper into the graphs of them, but also take some time to set the stage of what it means where different numbers are in different places in the equation and all the information that tells us about what the graph looks like, okay? I know it seems silly right now where we're like, we have graphing calculators, we have tools that can help us graph things quickly, so why would we need to know what they look like? And the short answer is that when we get to Calc 1, so Math 150, or if you also then want to go on to Calc 2 or Calc 3, knowing what the graph shapes look like make learning everything else easier. Okay, so the better you know these shapes, the easier it is for you to learn more information about those shapes in the future, okay? All right, so like I said on Monday, I like to always start with what we know and then kind of talk about what's new, okay? So what we know is a y equals mx plus b situation, all right? Or an f of x equals mx plus b. So what does the m stand for in the equation? The slope? Sure does stand for the slope. And someone else maybe tell me about the b value. What does the b value tell us?
The Y-intercept.
It does give us the y-intercept. Perfect. All right. So these are things that we know. And we also hopefully know that we could have sort of like 4 different types of lines, right? So let's say I drew a line that looked like this. Okay. Tell me about the slope of this line. Positive slope or negative slope? Yeah, it is a positive slope. All right, so below this, we could write positive m. What about the y-intercept of this graph? Positive or negative? Negative, right? Because it crosses down here. So we have a negative b. All right, so a positive slope, but a negative y-intercept. All right, what if I drew a line that looked like this? All right, what do we have for the slope and what do we have for the y-intercept? Positive or negative? Negative slope, I agree. Yeah, and a positive b, good, thank you. All right, so negative slope, positive y value. And even though these things seem super easy to us now, maybe when we first learned them, we were like confused about which one was which, or, there's a lot of things that maybe were hard in the beginning that we've forgotten were challenging for us. All right. But we've got 2 more types of lines that actually are going to be pretty important to us as we continue in our math career. Okay. So let's say I had a line like this. Okay. Somebody tell me about the slope of this line. Ah, slope of 0. I see a slope of 0. I see an undefined. This is the question, right? We know the positive and negative slopes so well, but it actually turns out that slopes of 0 and slopes of undefined are actually going to be maybe a little bit more important for us, especially when we get to calculus. So knowing which one is which is going to be really important here, okay? This line, this vertical line, has a slope that is undefined. All right, so this is a slope that is undefined. And yeah, exactly, because there's more than one value of a y for every x value, okay? Now, one of the things that I am very picky about is notation, okay? My job here is to make sure you have access to all of the math that is to come that you want to take. All right. And part of being able to access that math is having really accurate notation. So when we write equations for these lines, the vertical ones, I don't want us to just write a number. I want us to write it at like x equals whatever number it is. Okay, so if you don't have an x equals there, I'm going to take off points. All right, we need to know the difference between it's just a number and x equals a number. Okay, so when we have x equals a number and we're looking at the equation, that means it's a vertical line. Okay, but on the flip side, if we have something like this, what is that slope? And what is the equation? Yeah, this one has a slope of 0, okay? What about the equation of the line? Yeah, it's not going to be x equals the number, it's going to be y equals a number, okay? So one of them is x equals the number, the other one is y equals the number. And at this point, it's not enough to remember, oh, it's one of the two. I really want you to know which one's which, okay? All right, so that's what we know, a little reminder about that. But let's go back up to the other side now and talk about what's new, okay? So newish, because we kind of talked about it on Monday. So from Monday's lesson, we see f of x equals ab to the x, and immediately we are thinking, this is an exponential function, okay? And we knew that there were two types of exponential functions. But what we're going to do for the purposes of 4.2 is we're going to say let a equal 1. Okay, so we're going to imagine that a equals 1. What does that change the ab to the x equation into then, if a equals 1? Yeah, it's just going to be b to the x. Very nice, right? Because a goes to 1, and so the only thing that changes now, we have f of x equals b to the x. Beautiful. Okay. So when we graph these, we're still going to get a situation where maybe we have, what is this called again? When it starts flat and kind of goes up. It's an exponential, but this is specifically an exponential growth. Good, okay? I have not drawn the asymptote yet. It's there, but I haven't sort of highlighted it, okay? So this one does have a horizontal asymptote, okay? And the equation for this horizontal asymptote is going to be, oops, we want to use the proper notation. We go back, we realize this green line is horizontal, and so is this last linear one we drew. So we know it's going to be y equals a number. And so our horizontal asymptote is going to be at y equals 0, okay? Now, what about the coordinate for this point? What is the coordinate of that point? 0, 1. Good, very good. So we can write that in, that it's going to be 0, 1, okay? Now, tell me about the b value for this graph. What kind of numbers do I know are going to be potential b values for this graph? They're going to be greater than 1. Good, very good. Okay, so I know in this case that b is greater than 1. I know that this is an exponential growth function. All right, two last things. Tell me about the domain and tell me about the range. Yeah, the domain is going to be from negative infinity to positive infinity. All right, so from negative infinity to positive infinity, because it stretches sideways forever and ever. Okay, there's no x value that I can't put in there. Now the range is only going to be positive numbers. And so we said we're going to do a parentheses because we don't include the 0. And then to infinity, and then we close it, okay? All right, so we've got this as our exponential growth, and then we followed it with an exponential decay. And with the exponential decay, we knew that it kind of started up here and then it went down and flattened out. And a lot of the same features from the growth we can write down here for the decay. So this is going to be 0, 1 again. I still have this horizontal asymptote. And if I work from the bottom here, I can write that my horizontal asymptote is y equals 0. We want to be thorough, right? At y equals 0, not just 0. We know that our domain and our range are actually the same here. It goes forever sideways, and then it starts just above 0. It doesn't include 0, and it goes all the way to infinity. Now, we called this one an exponential decay, and we didn't say that b was just less than 1. I meant to write 1 here, not 0. Sorry. B is greater than 1. B is not just less than 1, but it is actually between 0 and 1, okay? All right, so let me zoom out for a moment, but that's what we have for sort of lines and exponential curves, okay? So our main focus for today is going to be two things for this section. First, we're going to practice plotting some exponential functions. I'll talk about what features I really want to see, because at some point we're going to get a lot of decimals and I don't need you to graph every single point, okay? And then the second focus for 4.2 is we're going to talk about graph transformations. And this really sets the stage for a lot of what we're going to be doing over the entire semester, okay? So let me zoom back out. Let's take a look at this particular example, okay? So we've got graphing exponential functions. So we have f of x equals 2 to the x. Now, I want us to plot a few more points than we did on Monday. And this time we're going to go from -3, -2, -1, 0, and then 1, 2, 3, okay? You don't have to split your table like this. Honestly, it just didn't look as good when I made the table go all the way across the page and then have the graph underneath it. So that's why I split it into 2. But you could just write it as one XY table, okay? But one of the things that was easy for us on Monday is when we plugged in 0 or we plugged in positive numbers, we knew what that was equal to. So for example, if I plug in 0, 2 to the 0 is going to be 1. When I plug in 1 for x, 2 to the 1 is 2, and then 2 squared is 4, and 2 to the third is 8, okay? And those I know you know how to do, okay? But the part that trips up a lot of students is this -3, -2, -1. And I even remember someone was really brave, put out an answer, was like, is it like a negative number, or is it like, you know, it was just a little bit hard. Sometimes we don't remember the rules. So what we talked about on Monday was that it was really the same thing as saying like 2 to the -1 power is really 1 over 2 to the 1. Okay, so going back to those exponential rules, that this would be 2 to the -1 or 1 over 2 to the first power. And that those were the same thing. And so that means that when we plugged in -1, we actually got 1/2 for the y value. What did we get when we plug in -2 for the y value? Thank you, Richard. I just saw your message. Yeah, it's going to be 1/4. And what happens when we plug in -3? 1/8. Excellent. Okay. So when you guys are studying, okay, I think sometimes we like to study things that we know because it kind of makes us feel good. We're like, oh, yeah, I know this, I know this, I know this. And sometimes we forget to spend some time practicing things that we're not quite so good at. So for example, if I were a little bit nervous about negative exponents, I might make sure to add that to my list of things I should study up on a little bit more, because I don't want that to be the one place I make a mistake on the test, okay? All right, so now that we have our coordinate points, let's plot them. So I'm going to start over here. Okay, so I've got an x value of 3, and I go all the way up to 8. All right, so 3, 8. And then my next pair is going to be 2, 4. And then my next pair is 1, 2. Okay. Then I have 0, 1, negative 1, 1/2, negative 2, 1/4, and negative 3, 1/8. Okay. So as we go to the left, the points get closer and closer to 0. And as we go to the right, the points keep getting bigger and bigger and bigger. Okay. So let's connect all these points with a nice smooth curve. All right. So if we were just plotting exponential functions from a table, we could always do something like this, okay? No matter how complicated it gets, you can always use an XY table. But my goal for sort of our next section is I really want us to get quick at graphing these so that we can sketch it maybe even quicker than we could type it into a graphing calculator, okay? But before we do that, let's try one more example. So we've got g of x equals 1/2 to the x power, okay? And we're going to try the same x values, negative 3, negative 2, negative 1, 0, 1, 2, 3, okay? So let's start with maybe what I think is the easiest one. What's 1/2 to the 0 power? Yeah, it's going to be 1. Excellent. I love how well we know that. What if I put 1/2 to the 1 power? I think that one's pretty obvious. We've got a 1/2. But what if I have 1/2 to the 2nd power? Yeah, 1/4. 1/2 to the 3rd power? 1/8. All right. So those, even if I don't know what to do with the negative exponent part, write down the ones that you know. Okay, that's actually a really good test taking strategy, is to kind of just write down something. All right. I have one student who started with me in STEM core last year, and we just finished. He went all the way through the STEM core program, and then he took Calc 2 with me during the summer. So he's already in Calc 3. So a year from now, you guys could also be in Calc 3 already, okay? Which is kind of crazy to think about. But I bring up this particular student because in the beginning, he was so bad about not writing anything down. If he didn't know it, he would just leave it totally blank. And when I was grading his tests, if it's totally blank, I gotta take off all the points. Like, there's not even anything I can try and do to help you out. And so that was a real big growing point for him, because when I graded his Calc 2 final exam, he didn't leave a single thing blank. And that content was so much harder than what we had learned in STEM core, but he just learned how to like push through, be uncomfortable, and kind of just write something down even if he wasn't sure. Okay, so that's one piece of advice that I'm going to kind of give to you there, which is I would encourage you to just write down what you know, right? And then kind of go from there. So let's see what happens if we plug in a negative 1. Let me write this up here. So 1/2 to the negative 1 power. How can we simplify this? What are some ideas that folks have? 1 to the negative 1 and 2 to the negative 1. All right, I love that. Distribute, distribute, right? That's something that we know how to do. Even if we don't know where it's going to get us, at least try the distribution. So 1 to the negative 1 over 1 to the negative, oh, my goodness, 2 to the negative 1. Okay. What happens from there? I think this is where we really need to think about what we do with negative exponents, okay? So with negative exponents, okay. So Christina, if we want to subtract exponents, then what we would need to have is that this base and this base would have to be the same number, okay? But right now we have a 1 and we have a 2, and since those are different numbers, we can't subtract the exponent, okay? But Eric says move it to the denominator and move from the denominator to the top. Okay, so I think what you're trying to say, and correct me if I'm wrong, is you want me to take the 1 to the negative 1 and move it to the bottom of the fraction, and then it'll become 1 to the 1, and then take the 2 and move it to the top of the fraction, and you'll get 2 to the 1. Okay. So that I think is actually a really great strategy here. So when we have negative exponents, okay, let's say if I just had 3 to the negative 5, I think we would all know that we need to write it as 1 over 3 to the 5, right? If we have the negative exponent, we can write it as the same exponent but positive. And I think a lot of times in high school, we learn it as you move it to the denominator. But what I want to reframe for us is we actually move it to the other side of the fraction line. Okay, so we're almost imagining there's a fraction line here. There's over a 1, and we're going to move it to the other side of that line. So this 1 to the negative 1, I'm going to move down here, 1 to the 1. And with this 2 to the negative 1, I'm going to move that to the other side of the fraction line, which will be 2 to the 1. And that we can simplify to 2. All right. So let me go back into the chat for a moment. There were quite a few ideas, and I just want to make sure we've hit them all. Natalia said, since they are both negative, find the reciprocal. Is that what you meant by like sort of flip the top and bottom? Yeah, okay. And then Ashley said cross multiply. Can you say something a little bit more about that? I'm not sure what you mean by that, but we can come back to that later. Laura said we could try multiplying by 2 since it's in the positive direction. Okay, so yeah, I mean, one pattern you could also see is like, how do you get from 1/8 to 1/4, right? So you're multiplying by 2, you're multiplying by 2, you're multiplying by 2. So then if we kind of keep with that pattern, we know the next numbers are going to be 4 and 8, okay? But if we think about how we handle exponents, let's make sure we know how to get there. Okay. Eric said, can you just flip the fraction and make the exponent positive before you distribute it? Okay, so if you are going to flip the fraction, yeah, it's going to be 1 over that fraction, which is flipping the fraction. So you could do flip the fraction to the positive exponent. And that will maybe a little bit faster, get you right to the number. All right, Richard said, doesn't one have to the, if you simplify and turn it into a positive exponent. Is that kind of what you meant too, Richard? Yeah, okay, cool. All right, so let's practice maybe this second strategy. I think it's a little bit faster than what I did the first time. If I have 1/2 to the -2, okay? So 1/2 to the -2, let's use the idea that folks had, which is flip the fraction first, 2/1, and then that's a positive exponent now. And so that confirms Laura's idea that this is going to be a 4, that I could just multiply the 2 by 2 and get 4. Okay. Now let me just show it one more time with the third power, just so we can practice our work with exponents. If I have 1/2 to the -3, that's the same as 2/1 to the +3, and that gives us 8. Okay. Now, positive and negative exponents come up so much in calculus, like so much, okay? So being able to work with positive and negative exponents is going to be a really helpful skill for us to develop this semester, okay? So now that we have our points, let's go ahead and plot them. We've got a -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, and 3, 1/8. All right, well, this gives us what we call an exponential decay. Okay, and we could have known from the beginning that it was going to be an exponential decay because this is our b value, and b is between 0 and 1. Okay, so even before I plotted the points, I could tell, hey, this is going to be an exponential decay function. All right. Okay, so now we're going to be doing a lot of graphing. The goal here is not to rely only on a table every single time. Okay, so by the end of next week, I want us to be really good at sketching these shapes without having to make a table. Okay, so when you sketch a shape of an exponential function, these are the features I would like you to include. All right, it's not point by point by point, but I want to see what I'm going to call in parentheses the x-intercept, or sorry, the y-intercept. Okay, now what I mean by that is this point right here, our 0, a. I want us to keep track of where that point is. All right, it's not always going to be where it crosses the y-axis, especially if we move our shape side to side, it's going to change. All right, so I'll explain that later in a little bit, but it's not always where it crosses the y-axis. It's where this point started and then where you move it around the graph. So that's one thing that I'm looking for. I also want us to write it as a coordinate, meaning 0, a, or whatever the coordinate is, write it as like something, something else, right? The other important feature I want us to have is the general shape. By general shape, I mean it's either growth or it's a decay. All right, you don't have to plot any more points than just that one quote unquote y-intercept and the shape. Okay, the last thing I want us to include is that horizontal asymptote and equation. And just as a reminder, we never want to write it just as a number. We're going to write y equals a number, whatever that number happens to be, for our horizontal asymptote, okay? So 3 things when you're doing graphing on like any of the quizzes or any classwork or on an exam, those are the 3 characteristics I'm looking for, okay? The y-intercept, a general shape, and the horizontal asymptote and equation. All right, any questions so far? All right, so let's move on to this second section called graph transformations. So graph transformations, we're really asking ourselves the following questions. What do numbers in different places of the equation tell us about the graph of the function, okay? So what we're going to start off with is writing our, what we're going to call a parent function. So f of x equals b to the x, okay? So this is something called a parent function, all right? And the parent function is just that special case when a equals 1, all right? So we've just got one of the 2 graphs we saw earlier. It either grows or it decays, and that y-intercept is at 0, 1, okay? So that's sort of our general graph, our basic graph. And next week, we're going to learn a lot more basic graphs that we tend to see a lot in all these math courses that are coming up. So the graph transformation form looks a little bit more complicated, okay? It looks like this. F of x equals a, capital A, lowercase b. In the exponent, we're going to have a capital B, parentheses, x minus capital C. And then back down on the regular line, we're going to have a plus d. Okay. All right. So if you see a number in for A, a number in for B, a number in for C, or a number in for D, those are going to tell us different things about our graph, all right? And the goal of this section is for us to understand, if I see this number here, what does it look like on the graph? If I see a number there, what does it look like on the graph? What if it's positive? What if it's negative? What can I tell from the equation, okay? So the question I'd like to ask you is this. If you plug in a number for x, right? So let me just highlight the highlighter and the pen are like right next to each other, and sometimes I just hit the wrong one. Okay, so let's do this. If I plug in a number for x, I substitute a number in for x. What order should I complete all the operations like plus, minus, multiply, divide, so that I can find f of x, okay? So if I plug in a number for x, which of those capital letters do I use first? A, B, C, or D? All right, I have 1 vote for a C. Anybody else? I see a B, okay. All right, so folks who are saying B, tell me about your reasoning for that. Like, why do we move B first, or why do we use B first? And then folks who are saying C, tell me why C. Okay, I see C because it's in the parentheses, PEMDAS. Okay, and then someone says distribute the B. Okay, so the B applies to X minus C, but if we're not going to distribute anything, then folks who said C, you are correct. The first thing we're going to do is simplify inside the parentheses, okay? So the first thing we're going to do is take care of the C value. All right, after we simplified X minus C, what is the next capital letter that we would use to help us find our f of x? Excellent, now we go to the B, all right, because we didn't distribute it yet. So now we're gonna go to the B value. All right, so that is the second one in the order. All right, let's keep going, folks. After we simplify B times X minus C, what's the next capital letter that we need? Hey, excellent. All right, so we've got C and then B and then A. And then that leaves nothing else but D at the very end. Okay. So folks, what you've just been able to tell me is the order in which the graph transformations happen. Okay, so when we talk about graph transformations, what we mean is we're going to be moving the graph around, like the picture of the graph, around the XY coordinate. So we might move it up, we might move it down, we might slide it to the right, we might slide it to the left. Sometimes we can stretch them up and down. Sometimes we can stretch them side to side. All of those things we know from what A, B, C, and D are. Okay, so with that being said, let's write out what C, B, D, and A stand for. Okay, so the first thing we're going to do when we look at a complicated looking equation like this is we're going to say, hey, what's that number C? All right, and in the equation, if you have X minus C in the parentheses, what that means is you are going to move the graph to the right C units. Okay. Now, if you happen to see in the equation X plus C, that means that we're going to be moving things to the left C units. Okay. The B value is going to be a case where we might stretch or compress the graph horizontally. Okay, so if B is greater than 1, then we are going to have a horizontal compression. And if B is less than 1, we will have a horizontal stretch. Our A value, if A is greater than 1, that's going to give us a vertical stretch. And if A is less than 1, it will give us a vertical compression. And last but not least, that letter D is telling us if we have a plus D at the end, that's going to move it up D unit. And if we have a minus D at the end, that's going to move it down D unit. Okay. So I know there's a lot of sort of rules that I'm throwing at you right now, right? I'm like, here's this equation. I'm going to tell you what all these things mean. But what we're going to take a look at in the next few pages is how we can see from the equation, like what things are moving and what things change and what things stay the same. And yeah, I am a huge nerd and I love seeing how like a number here can tell you exactly what it looks like. Like that's pretty cool. That means that you are smarter than a calculator because you can do it more quickly. You understand not just what it does for one graph, but for another graph. So Eric, that's a really good question. Capital A is not really different than the little a, but not every parent function we're going to look at has a little a in the front. And so mathematicians have sort of decided, hey, all the capital letters will talk about the graph transformation. So for the exponential one, it's not actually different. But when we look at the log graphs at the end of class, I think you'll notice there's no little a in the front, but the capital A will be in the same place. All right. So let's take a look at more detail about each one, okay? So we've got 3 graphs here. I think from these graphs, you can all see that they're exponential growth, right? All 3 graphs start kind of flat and then they go up pretty quickly. Now, which one of these 3 is the parent function? Can someone tell me? Is it the purple one, the red one, or the green one? And how do you know it's the parent function? All right, red, pink. All right, cool. Yes, the red one because of the Y-intercept. All right. Now, one thing that you'll learn about me is I really like you to be able to explain why. And it's not from a like gotcha kind of perspective. Like I'm not trying to catch you in a moment where you don't feel like you understand something, but it's actually the exact opposite. I want to make sure that you're making decisions for the right reasons, and so that that reasoning can carry forth, and it's not like you accidentally learned one rule for one thing and it doesn't actually carry over to other graphs. Okay, so this one is indeed our parent function. So in case you can't tell, I love having different colors on my tablet. It's actually one of the things that I'm like, I don't like teaching remote. I don't think that it is as effective necessarily, but I really like having access to so many different colors on my notes. I think this makes it like a lot easier for students and for myself to like stay organized. In the classroom, I only have 4 different colored markers and I'm always like, oh, that really sucks. It's only 4 colors. But here we have like a bazillion different colors. All right, so we've got our parent function. We know because it's 0, 1 for the Y-intercept. All right, okay, so earlier I said when you sketch graphs, I want to know about the shape, right? So we can see these are all growth. I want to know about the horizontal asymptote, but I also want to know about the Y-intercept. And I put that in quotation marks because I was like, it's not always the Y-intercept. So for the green curve, okay, I want us to see, like, if I took this blue point and I moved it over, it would get moved over to here. So what I've done is to get from the red curve to the green curve, I've completed a horizontal translation or a horizontal shift. This blue point is the one that I would want you to write the coordinate for, because that is the y-intercept of the parent function, and it's where it got moved to. So let's practice writing that coordinate. This coordinate is not 0, 1, but rather it is 3, 1. Okay? So if you were sketching a graph, you were sketching the green one, that is the point I would want you to label, is the where the y-intercept got moved to, 3, 1. Okay? What is the quote unquote y-intercept for the purple graph? -3, 1. Yeah, exactly. Because if I slide over to the left 3 units, I get to here, which is -3, 1. Beautiful. Okay. Now, all 3 of these graphs, do they have the same horizontal asymptote? Yeah, they do, right? This asymptote is going to be right here at y equals 0. Okay. So when we have these different graphs, okay, let's actually think about what the equation for this one is. So the equation for the red one is y equals b to the x. Okay, so I don't know exactly what b is, but I know it's an exponential function. When I write the equation for the green one, I would write y equals b to the x plus or minus 3. Okay, so it is in the equation -3, okay? I know that's weird, but I think one thing to think about is that the horizontal shifts, I always get nervous, I'm gonna say that word wrong, but the horizontal shifts slide in the opposite direction than you think they will. So an x -3 actually goes to the right, whereas an x plus 3, which would be the purple one, moves the graph to the left, okay? So if we are to summarize that, we can say that our x plus c means we go to the left, c, and x minus c means we go to the right, c. Okay? Now again, I know we just wrote that like less than 5 minutes ago on the other page, but I think I am a big fan of the more you write it, the stickier it is in your brain. Okay, that's actually one of the studying techniques I do for my own classes. Like when I'm taking a class as a student, I will write things over and over and over again so that I really remember what it is that I'm doing. Okay. All right, I've got one last set of questions here, which is what changes and what stays the same? All right, so when we look at this graph from the red one to either the green or the purple, what changes and what stays the same? And let's think about our 3 characteristics that I want you to graph for each one: the y-intercept, the shape, and the horizontal asymptote. So of those, which ones change and which ones stay the same? Okay, the y-internet, sorry guys. The y-intercept changes by, and the horizontal asymptote stays the same, and the shape also stays the same. Great summary. All right, so what changes? We can say that the y-intercept changes, okay? And what stays the same, we can say that the horizontal asymptote stays the same and the shape stays the same, okay?
Can we also say that all x values change?
I understand what you mean, but I think that anytime we move it anyway, the x values are going to change. But I think we want to think about it like relative to itself.
Okay.
Okay. All right. So those are our horizontal translations. That's what we take care of first when we look at a graph transformation. Let's take a look at two examples. And I think for the sake of time, we're not going to sketch them, okay? But you can graph them on your own time to see if you've got them right. But let's take a look at this equation. F of x equals 2 to the x plus 1. Tell me what changes and what stays the same when compared to the parent function, and describe the graph transformation, okay? So when I look at this equation, I notice that we have this plus 1, right? That means that the only thing that happens to this graph is I move to the left 1 unit. All right, so that plus 1 means I move to the left 1 unit. What changes and what stays the same? That means that my y-intercept changes, but let's maybe be specific here. It was at 0, 1. What is the new quote unquote y-intercept? -1, 1. Great. So we can say a y-intercept of -1, 1. Perfect. And our horizontal asymptote at y equals 0, because that doesn't change. And one last thing, is this a growth or a decay function? It is a growth one, exactly. All right, and again, for the sake of time, we're not going to graph it right now, but I'll let you go ahead and graph that later if you want to. Right, okay, so I just want to clarify what I'm saying when I mean y-intercept. What I mean is like the new one, okay? So it's sort of like this blue point that traveled between all these graphs. That's what I'm calling the quote unquote y-intercept. I understand it's not the actual y-intercept, but that's the point that I think is the easiest to kind of move around, okay? Yeah, okay, that's actually a really good point, Eric. So is there another name? I think sometimes I call it the center point. So it's not that it is in the middle x value wise of the original one. Would it be more helpful if maybe we called it the center point? Yes, it is exactly for that reason, because it's easy to translate. It's the one point you know, so you can just move it around. Okay, maybe let's reframe this as a center point for right now. I think that language will actually carry through a lot better when we get through some of the other parent functions as well, okay? But yeah, we're really trying to make our lives easier. Pick the easiest point, move that one around, and then you know where to sort of start your graph, all right? All right, example 4 here, real quick, tell me what that -5 does. Exactly, it's gonna go to the right 5 units. Let's change our language. That means our center point is gonna be where? Yeah, it's going to be 5, 1. Our horizontal asymptote stays the same, so it's still at the x-axis. And is this one growth or decay, and how do you know? Yeah, it's a growth function. Very good, because that b value is greater than 1. Perfect. Okay. So by itself, this is not necessarily a big deal, right? Like just looking at one graph transformation at a time is not a big deal. But as we move on, we're really looking to be masters of when there's more than one graph transformation happening at the same time. How do we know what order and what all the different parts do? Okay. So let's take a look at the next one. Okay, so the next one is our horizontal stretch or compression, and that corresponded to letter B in our equation. I think this one is actually hard to see in our graph for the exponential functions, okay? But we're gonna try and give it a go. So when we're looking at these three graphs, I think it's a little bit harder to tell which one's the parent function, but it is the red one again. So we're going to assume that this is y equals b to the x, okay? Now, when we stretch or shrink something horizontally, we're really sort of looking at either stretching it that way or like compressing it in this way. Okay, so kind of like an accordion, we either pull it out to horizontally stretch it, or we smush it in to make it compressed. Which one is the horizontal stretch, the green one or the purple one? Yeah, the purple one, good. So this one is our horizontal stretch. Which means that our green one is our horizontal compression. Okay. So when we're looking at sort of what changes and what stays the same, I think that what stays the same, we still have our same center point because they all cross the y-axis or whatever we call our center point right there. That didn't get moved anywhere. We didn't move it to the right. We didn't move it to the left. So our center point stays the same. Our horizontal asymptote also stays the same, okay? But what changes is maybe not so much the shape, but we can sort of refer to it as the steepness of the curve, okay? So we can see that the green one is more steep than the red one, and that the purple one is less steep than the red one, okay? So when we're thinking about what changes or summarizing that, we could say that when B is greater than 1, we end up with a compression. So all the horizontal ones are the opposite of what you think they are. And when B is less than 1, we've got a stretch. Okay. So let's take that information and take a look at 2 more examples. And same thing, we're going to ignore the graphing right now for the sake of time, but let's talk through what happens in the graph, okay? So we're not going to sketch a graph. We're not going to sketch a graph, but you can do that on your own time if you want, okay? All right, so let's take a look at example 5. It says f of x equals 2 to the 3x plus 6. What's my b value? What's my c value? All right, I've got C is 6 and B is 3. I've got B is 2 and C is 6. And then we've got B is 3 and C is 2. Options. Okay, I love this. So I think a lot of folks, when they either read the question too quickly or then they're thinking that the C value is 6 because we see the plus 6, okay? But if I scroll back up real quick, one thing I want us to notice is that in our parent function, we actually have to factor out the B value. That horizontal stretch or compression, we have to factor that out so that the X value has the coefficient of 1, okay? So if I scroll back down, what that means is that we need to do some work to this equation before we can actually answer the question. So 2 to the 3x plus 6, if we want to write it in graphing form, is actually 2 to the factor out of 3, x, not plus 6 anymore, but plus 2. Okay. Yeah, this is probably the trickiest part to the graph transformations, the horizontal business right here where you have to factor that coefficient out, okay? But from here, I think we can tell that our graph is going to go to, it's going to go to the left 2 units. That's our C value or C value that happens first. And then it has a horizontal stretch or compression. Yeah, it is a compression. So we can say a horizontal compression of 3. We're squeezing it in 3 times as small, okay? Our horizontal asymptote doesn't change. It's still y equals 0, and we still know that this one is going to be growth, but it's going to be more steep than the parent function. Christina, the 6 becomes a 2 because I factored out the 3. Does that make sense? Like if I distribute this 3 back in, it's going to give me my original. Okay. And Antonio, when you say, how do you factor out the 3? Like you just think almost like backwards, right? Like, yeah, I think Natalia says it really well. Like 3 times what is going to give me 3x? Yeah, you divide everything by that 3, right? And 3 times what is going to give me 6? And 3 times 2 is going to give me 6. That's why there's a 2 there. Okay. All right, let's take a look at one more example and then we're going to take a break here, okay? So when we look at this one, we have 2 to the 1/2 x minus 8. So let me write that again down here, 2 to the 1/2 x minus 8. Now we know from our last example that we have to factor out that coefficient. So last time we factored out a 3, what are we factoring out this time? We're factoring out the 1/2, yeah. Now, I know that generally students don't like fractions as much as whole numbers, but I think it's really important that we know how to answer questions with whole numbers as well as fractions, okay? So 2 to the 1/2 and open up a parentheses. Now let me talk through this one a little bit more. 1/2 times what gives me 1/2 x? Yeah, 1/2 times x is going to give me 1/2 x. Now 1/2 times what is going to give me 8. And I already see a couple answers there. Yeah, 1/2 times 16 is going to give me 8. So this becomes minus 16. Okay. Now it's in a form where we can see our C value, just like we could see the C value here. And it tells us our B value, just like this told us our B value. And so we can say that this one goes to the right 16 units. And we have a horizontal stretch of 1/2. Okay. So we're stretching things out. My horizontal asymptote stays the same. And I know it's a growth because the B value is 2, the lowercase b value is 2, and we know that that means it's a growth function, okay? So I think this is a good place to take a break, all right? So it is 10:52 right now, so I'm gonna stop sharing my screen. I'm gonna resume the record, share screen. Yes, I am using Notability. So when we went remote in the spring, I asked some of my students like which ones they used for their notes, and so I heard a lot of good reviews about Notability. And at first, I was like, I don't know if I want to pay for it, but it's been worth it for me at least with the Notability. But I think the other one that folks use is called Good Notes. So if you have a tablet or you're thinking about going in that direction, Good Notes and Notability, I think, are two of the top apps out there for note taking. But I like this one, so cool. Yeah, that should actually make it super easy for you to submit your work via PDF because you can just export it right as a PDF. So that's awesome. All right, so let's go back up here real quick. This is really something that, like, when you're preparing your reference sheet for the exam, I would really encourage you to include this part here. I think it's a really good summary of what all the different pieces do, okay? And if you like the color coding, feel free to color code your own as well. Some people find it helpful, some people don't really like it, so, you know, no harm, no foul either way, but find something that works for you, okay? So we've talked about the horizontal components. We've talked about these two, our C and our B. And those are ones, because they're horizontal, they actually seem like they're doing the opposite of what you want them to do, right? Like a minus C actually means move to the right. But like a B value greater than 1 actually compresses your function. So now we're going to spend the second half talking about A and B, where we look at vertical stretches and vertical compression and moving a function up and down. And the nice thing about this is they do exactly what you want them to do. Something that's bigger than 1 for A is going to be a vertical stretch. Something that is a plus D is going to move up D. All right, so the horizontal ones are the opposite of what you think. The vertical ones are exactly what you want them to be. All right, so let's get on to our vertical stretch and compression. So we've got, this is our A value here. All right, so the A value in the general equation form, that tells you about the vertical stretch or shrink. Now in this case, we have our center point at 0, 1. So we know again that the red one represents our parent function, okay? Now, which one of these is the horizontal stretch, the green one or the purple one? Why are you saying purple? Yeah, when we're looking for a vertical stretch, okay, we're making it taller than it was before. And so when we look at this green one, we can actually see from our center point that it is taller than it was. Actually, let me do blue for that. Okay, so this green one represents a vertical stretch, all right? That means we've got some A value in the front that's bigger than 1. And the one that is the vertical compression, it's almost like it gets shorter. And you can tell that the Y-intercept, or the center point, gets shorter than it was, okay? So the purple one is our vertical compression. And if we think about the summary for that, we can say that when A is greater than 1, that is the vertical stretch, right? Well, makes sense. Exactly, the number is bigger, so then the vertical stretch happens. But if our A value is less than 1, we're going to have a vertical compression. Okay. Now, let's talk about what stays the same here. So if I think about the characteristics, like my Y-intercept or my horizontal asymptote or the steepness, which one of those stays the same? Yeah, that horizontal asymptote. All right, so our horizontal asymptote stays the same, but the steepness of our curve changes. And our center point also changes, okay? So center point and our steepness. The general shape stays the same, but the steepness of it is gonna change, all right? So let's take a look at 2 examples. Again, we're going to ignore the sketching for right now. We're going to focus on talking about the graph transformations, okay? So in this case, I've just layered on from our previous example. So right away, when I see my f of x for number 7, I'm going to keep the 5 in the front, times 2, but instead of keeping it as 3x plus 6, I'm going to factor out that 3 again and then have the x plus 2. Okay. Now I think it's easy for us to recognize our c value, our b value, and our a value. So let's list our graph transformations. We know that it's going to move to the left 2. We know that there's a horizontal stretch or compression of 3. Compression, good. So horizontal compression of 3. And now we have that new number in the front, the capital A, that 5, and that is going to give us a vertical stretch of 5. Okay. All right, so let's take a look at example 8, right? Now, same thing again, I've taken the previous example and kind of added a number in the front, or rather multiplied a number in the front, okay? So our f of x here, we want to go ahead and have that 1/6 in the front times 2, but we're going to factor out that 1/2. And like you folks very correctly told me, that gives me x minus 16, okay? So what does that tell us? That it moves to the right 16, that we have a horizontal stretch of 1/2, and we have a vertical compression because the vertical ones are the ones that are exactly what they look like, of 1/6. Okay. So let me zoom out for a moment so we get this all sort of on one page. Are there any questions about the vertical stretch or compression? Okay. So we've talked about C and B and A. Now let's talk about D, the last graph transformation. Okay. So for this one, I thought it would be kind of interesting to sort of draw our own one, okay? So we know if we're going to draw an exponential growth curve that it's going to cross through 0, 1. And the rest of it we can kind of sketch that it goes up like this and that it sort of flattens out down here, okay? So if you're drawing one on an exam, this is totally fine, all right? I don't need you to spend hours making it perfectly perfect. This is what we mean when we say a quick sketch, all right? So let's say that I had an equation where I had a plus d at the end. We know that means that we move our function up d units. And so what that might look like here is, let's say I wanted to have, instead of y equals b to the x, I wanted to graph y equals b to the x plus 5. Okay, so let's say we want to graph y equals b to the x plus 5. Well, I'm actually going to go back and draw in my horizontal asymptote here, okay? But when I think about things moving, we're going to go to that center point. And so, Eric, this kind of goes back to your point, like, why do we choose this center point to move? Because it's a nice value. And especially if we're shifting it up and down, it's nice to know where it's going to go. Okay, so this point is at 0, 1. But if I move everything up 5, that point is going to be at 0, 6. Okay, so my center point now moves up here. What else moves when I do a horizontal translation? Yeah, the asymptote, okay? So for pretty much all the other ones, it doesn't move. The one thing that gets it to move is that horizontal translation. So I'm going to sketch the new horizontal asymptote up here. And if I wanted to sketch this graph, I would just have one that kind of is flat and goes up like that. Okay, so there's my plus d unit. But if I do a minus d, I know that's going to move my graph down d unit. And so let's say this time that I moved the graph down 10 units, that I wanted to graph y equals b to the x minus 10. What's the equation of my new horizontal asymptote? Okay, all good guesses. My original asymptote was at y equals 0. I'm gonna move everything down 10 units for the purple one. Yeah, so it moves to where the horizontal asymptote is gonna be at y equals negative 10, okay? So the horizontal asymptote moved down here, but that quote unquote center point is not at 0, negative 10. It's at 0, negative 9 because we went 10 units down from the 1. So 1 minus 10 gives us 9. And then we can sketch the rest of it and say it's flat here, and then it goes up kind of like that. Okay? All right. So that's our vertical translation or vertical shift. And I think what we can notice here is that the center point changes. But in addition to that, the horizontal asymptote changes. Okay? But what stays the same is the shape. And we could even say that the steepness, if it's only a vertical translation, the steepness also stays the same. Okay? All right, let's do these 2 examples down here where we're going to unpack what happens in these graphs. Again, we're going to nix the sketching of the graph and just focus on identifying the transformations, all right? So with this f of x, tell me what graph transformations happen for 2 to the x plus 6 and then plus 1. All right, good. We move to the left 6, we move up 1, or we shift up 1 and left 6. I think because we know there's an order of operations, so to speak, for the transformations, I kind of like it a little bit better if we're saying that we move to the left 6 first, as a reminder that that's what we need to do first, and then we're going to go up 1 unit, okay? But they're both correct answers. So it moves to the left 6 and up 1. Any vertical or horizontal stretches or compressions? I think we can agree that there are not any, right? Because all those coefficients are just 1. Good. And then what can we say about example 10 here? What happens with example 10? To the right 8 and down 3. Excellent. We're going to move to the right 8 and down 3. All right. And same thing as number 9. There's no horizontal or vertical stretches or compressions. Yes, I'm sorry. So maybe we should go back and also say that the horizontal asymptote for number 9 is now going to be at y equals 1. Okay. And what's the horizontal asymptote for number 10? Y equals -3. Beautiful. I love it. Horizontal asymptote of y equals -3. Beautiful. All right. So we've got our C, our B, our A, and our D. All right. The last things that we want to consider with our graph transformation are these 2 questions right here. So what if B is negative and what if A is negative? Okay. So we've only considered sort of whether the numbers are bigger than 1 or less than 1, but I want to clarify that positive and negative are going to be sort of a different implication, okay? So if you have f of x equals b to the x, this is really saying b to the positive x, okay? But let's say that we had a different function that was f g of x equals b to the negative x. Okay. This is what I mean when I say when the b value is negative, right? So the number in front of the x is negative. Now, this graph for f of x, if we were to sketch a quick graph, all right, we know that f of x is going to start down here, go up like that, okay? But with our g of x, all right? This minus sign actually tells us that we're going to reflect over the y-axis, okay? Now, the reason why it tells us that is because we're saying for every x value that was positive, now you're going to make them negative, which means that they're on the other side of the y-axis. So instead of having a growth function, what we actually end up with is, well, sort of a decay function, because we've taken our original function and flipped it over the y-axis, okay? Yes, great connection. So if we have a negative a, that's going to reflect it over the x-axis. Very, very nice. Okay. Now, before we get there, let me just show you one quick example because I think this will be really helpful for the quiz. So let's say I have h of x, so another function, and we'll say that it's going to be b to the 11 minus x. Now, when we think about our graph transformations, we still need to factor out the coefficient of x. We want that coefficient of x to be positive 1, not negative. So what we need to do here is, I like to take a step where I rewrite it as negative x plus 11. And then I factor out that negative 1. When I factor out that negative 1, that's going to give me negative times x will give me negative x, but it's not going to be a plus 11. Right? It's going to be a negative 11. Okay? This is the #1 place that students mess up. Okay? I don't want that to happen to you. That's why I'm making like a big deal of this. We're going to factor out that negative sign, and then we can talk about the graph transformations. So this particular function moves not to the left 11, but it actually goes to the right 11. So if we don't factor out that negative sign, we actually get the graph going in the wrong direction, okay? So it goes to the right 11, and it reflects over the y-axis, okay? So when you see a question like that, do not fall for that trap. Make sure that you factor out that negative sign, okay? All right, and let's take a look at what happens when a is negative. So we'll go back to our good old f of x equals b to the x, and then we'll call our g of x equals negative b to the x, and compare those two pictures. And from all of our lessons, we know super well that that is our exponential function. And just like Laura said, when we have that negative in front there, this negative is going to reflect over the x-axis. So that's going to mean that our graph looks something more like this. Okay. All right, so that brings us to the end of graphs of exponential functions, all right? Are there any questions on this particular section? The little a for the exponential is the same as the capital A, Eric. However, in other functions, there might not be a little a, so then there's nothing to compare it to, okay? So little a and big A for exponential functions are the same. All right, and Natalia, is the horizontal asymptote the same? Yes, it is. So if we go back and highlight that in, we've got a horizontal asymptote here, and we've got one over here. Okay. All right, folks, I'm going to stop sharing my screen.